Let's take a look at this hypothesis testing problem. We have, in this case, a hypothesis test. This is a hypothesis test involving proportions. Specifically, it involves two different proportions, so it is a two-sample problem. It is a one-sided hypothesis test, or equivalently a one-tailed hypothesis test, because the question is if machine 2 is superior to machine 1, and because this is a proportion problem, it involves the test statistic z. So in our case, the null hypothesis is going to be that the difference of the two proportions is equal to 0. In other words, the two proportions are the same. Whereas the alternative hypothesis will be that the first one does not meet specifications as often as the second, and so that P1 minus P2 is less than 0. Before getting started on this, let's put down a few things that we need to know. The observed proportion for the first machine is 960 divided by 1,000, which is 0.96. The observed proportion for the second machine is equal to 582 divided by 600, which is equal to 0.97. And therefore the pooled proportion under the null hypothesis is equal to the total number of successes, which is 960 plus 582, or 1,482. I'm sorry, 1,582. Did it again, 1,542 divided by 1,600, and that works out to be 0.96375. So the standard error that we'll need for this difference of two proportions is equal to the square root of 0.96375 times 0.03625 times 1 over the first sample size plus 1 over the second sample size. And that works out to be equal to 0.009652. So the test statistic z is equal to the observed difference of 0.96 minus 0.97 minus the expected difference of 0 divided by the standard error for the difference, and doing the arithmetic, that works to be negative 1.03605. At this point, there are two ways of deciding whether to retain or reject the null hypothesis. We have a default value of alpha of 5%, and so the area under the fifth percentile of the normal distribution is 1.6449. In our case, 1.03 falls over here in the area that is not shaded, and so our decision will be to retain the null hypothesis or fail to reject the null hypothesis. The second way of proceeding is by finding the area to the left of negative 1.03605 and find the p-value, the observed significance level. And the area to the left is equal to 0.1514 using either the normal CDF command or else the command norm sdist. That is bigger than alpha, and so our decision will be to, again, to fail to reject the null hypothesis. We fail to reject the null hypothesis. We do not have enough evidence to think that machine 2 is better at meeting the specifications. And so that is the first part of the problem. The second part of this problem asks to determine the probability of incorrectly deciding that the two machines have the same rate of meeting specifications if machine 1 is inferior, and machine 1 meets specifications 95% of the time, while machine 2 meets specifications 97.5% of the time. This one is basically asking for the value of beta. What's the probability of retaining the null hypothesis, believing that the machines have the same rate, if there is a real difference in the rates? So we're asking for the value of beta, the probability of making a type 2 error. Now, based on the form of the alternative hypothesis, we know that we should use the form where P1 minus P2 is less than 0. So we remember that the alternative hypothesis was that P1 minus P2 was less than 0. And so we need to use that choice when figuring out the value of beta. And so just writing out the formula, we get that beta is equal to 1 minus phi times minus z sub alpha times the square root of p bar q bar times 1 over n1 plus 1 over n2 minus p1 minus p2, all divided by the square root of P1 Q1 over N1 plus P2 Q2 over N2. Now you'll notice that something's different about this problem comparing this one to the one where we did a difference of two averages. The standard error in the denominator is now different than the standard error that I had before. Here I have P1 and Q1 separately. These are not pooled. I pooled those together in the first part of this problem when I was deciding to whether to retain or reject the null hypothesis. Okay, now in the formula here, P hat is equal to, or not P hat, P bar is equal to the first sample size times the assumed probability plus the second sample size times the assumed probability for that one divided by the total number of samples, so 1600, and this works out to be 0.959375. So we get a big mess. I will write down the numbers that we have in our problem. This will be equal to negative 1.6449 times the square root, big square root, of 0.959375 times 1 minus that, 0.040625 times 1 over 1,000 plus 1 over 600 minus the difference. So minus 0.95 minus 0.975 all divided by another big square root. 0.95 is my assumed value for P1 times 0.05 divided by the sample size of 1,000 plus 0.975 times 0.025 divided by 600 and close parentheses. So we get this is equal to 1 minus phi of 0.87677, doing the arithmetic. So we need to find the area to the right of that number. Phi always gives the area to the left, and so I need the area to the right of 0.87677. And using a calculator or else using Microsoft Excel, this works out to be 0.1903. So there is a 19% chance of making the wrong conclusion if machine 1 works 95% of the time, while machine 2 works 97.5% of the time. Finally, we got an answer of 19%. Suppose that we really want the answer to be 1%. So find the number of times that the machines must be tested, assuming that we test them the same number of times, if I want that probability to be equal to 1%. Okay, so there's a formula for this one, and let me just write it out. The formula goes that in the case of a one-tailed z-test, n is equal to z sub alpha times the square root of p1 plus p2 times q1 plus q2 all over 2 plus z sub beta times the square root of p1 q1 plus p2 q2 all divided by p1 minus p2 whole thing squared. Now we have all the information that we need for this problem except for the value of z sub beta. So for that, we want the area in the right tail under the bell curve to be equal to 0.01, and that's the 99th percentile under the bell curve, and that works out to be 2.3263. Okay, now let's refresh our memory. From part 2, we had that P1 was equal to 0.95, while P2 was equal to 0.975, and the Q values, as always, are equal to 1 minus the P values. So this will be equal to 1.6449 times the square root of 0.95 plus 0.975 times the sum of the q's, so 0.05, 1 minus 0.95, plus 1 minus 0.975, which is 0.025, all divided by 2, plus the value of z sub beta, 2.3263, times the square root of P1, 0.95, times 1 minus 0.95 is 0.05, plus P2, 0.975, times 0.025, divided by the difference, 0.95, minus 0.975, and then it is necessary to square this entire thing. And then doing the arithmetic, this works out to be 1,800 1,816.86. And so rounding up, we get the n value should be 1,817. So that is the number of tests that must be done for each one if we want the value of beta to be equal to 1%.